I will cover the classical theory of exponential sums due to Weil and van der Kerkhout. It's quite old already, maybe nearly 100 years. So, title is Exponential Sums. I have to omit a lot of details, I have to say, to cover this classical theory. If time permits, I will go a bit further. I could look at the work of Bombay Ivanets, producing new exponent pairs, or maybe also I could look at p-adic exponent pairs. But let's see if that is possible. So, yeah, what are exponential sums? So we have some interval AB. Let's take I equal AB half open. And we want to follow the convention that A and B are positive integers. So A less than B, AB element N. And we have some nice function called amplitude function. Nice function. F from AB to R. So by nice, we usually mean often enough differentiable. And F should also satisfy some properties. We come to that later. Then an exponential function, exponential sum is the following form. Sums of the form. So n runs over the interval AB, A less than n, less or equal B, E of Fn. And so this notation means, as usual, E of z is e to the 2 pi I z. So this lies on the unit circle in the complex plane. 1 minus I, axis. Yeah, so that is the angle, basically. Z divided by 2 pi I rather. Is the, okay, sorry, 2 pi Z. 2 pi Z. It's this angle, and this is E of. Okay, and we see that this E of Z just depends on Z modulo 1. So that is only on that. So now, what is the task? We want to get non-trivial bounds for these exponential sums. So these values, E of Fn, will be somewhere on this unit circle. When we have an equidistribution of these Fn's modulo 1, then we can expect a lot of cancellation. So if Fn is completely randomly distributed, then we may expect this to be of size interval length square root about. Yes. Totally randomly. Distributed. Odd 1. We should have an element I, E of Fn, is bounded by interval length B minus A to the 1/2 plus epsilon. And in fact, there are many situations when we expect this behavior of exponential sums. There's the so-called exponent pair hypothesis, which implies that in many situations. But we are quite far away from proving that in typical situations. So in general, our goal is just get a non-trivial estimate. Let's call it S. Of course, the trivial estimate is just obtained by triangle inequality. S is bounded by, or is actually less or equal B minus A if we follow the convention that B and A are integers. Otherwise, we need to add 1. So that's important. This +1 is often important. Na gut. Yeah, so where is it useful in analytic number theory? In many connections. Let's recall some of the applications. First of all, it appears frequently in the analysis of error terms. That's because the box function often appears in error terms, and the box function can be approximated. Then we are left with some error, and that error can be Fourier developed. Often error terms can be estimated using exponential sums. Yeah, so as I said, often the box function, when we write down the error terms explicitly, yes, error terms. And so that function x minus box minus 1/2 called psi x appears when we approximate this box function by x minus 1/2. Yeah, set. So psi x. Yes. We approximate box function by x minus 1/2. Yeah, so this function psi x, the so-called sawtooth function, looks like that. 0, 1, 2, 3. So that's periodic. Average is 0. Yeah, so therefore we have the possibility to develop it into a Fourier series. At least this works outside these discontinuities here. In that way, naturally, we are led to exponential sums. So when we have, after analyzing error term, sums like that, then after Fourier developing psi, we are led to sums of that form. And psi h fn. I will make that more precise later on when we deal with applications. Sorry, E off. Okay, so that's a frequent application, analysis of error terms. Also, exponential sums appear directly when we look at the zeta function, when we, for example, try to prove subconvexity bounds for the zeta function. Convexity bounds for S. Okay, how does it arrive? When real part S is greater 1, we have a series expansion of the zeta function. If zeta S, if real part S greater 1, zeta S is equal to n equals 1 with t n to the minus s. So that doesn't work when the real part is less than 1. Nevertheless, partial sums of that form can approximate the zeta function in the critical strip. If 0 less than real part S less than 1, then still approximations of the following form are good. Yeah, we take n less or equal some parameter capital N, n to the minus s. Good. Naja, you can even do better if you use the approximate functional equation. You can approximate it by a linear combination of such a term and another term where s is replaced by 1 minus s. Okay, so we can boil down subconvexity estimates to estimating these sums, and they are actually exponential sums because over let's say S is sigma plus IT, so equal n. N to the minus s is equal to n to the minus sigma times e to the minus t I log n. Okay, and that can be rewritten in that form here. So this is n less or equal n to the minus sigma e of e log n divided by 2 pi. So this is a smooth weight. That is not a problem, can be removed using partial summation. Essentially, we are left with these sums here. So that is a direct application of exponential sums. Also in the theory of equidistribution, modulo 1, exponential sums come into play. So I will not define equidistribution and so on and so forth. But as I said already, yeah. When these fn's are equidistributed modulo 1, then we can expect a lot of cancellation in the sum of E of Fn. And we have even a criterion in the other direction, Weil's criterion. So Weil's criterion says if some n less or equal n, E of H Fn is little O of n, tends to infinity, for every H element Z without 0, then the sequence Fn is equidistributed modulo 1. One. Yeah, so now I take a sequence of fn's, infinite sequence of fn's. And we have this nice criterion here. And yeah, these are really exponential sums here. We need to prove a non-trivial bound for every h. Yeah. Yeah, so that needs to be chosen suitably. So one can express directly, one can express precisely that as this is equal to that, plus some error term, which depends on n. Na gut, so we see that exponential sums are extremely essential in many connections. Good, so then let's start the theory. Let's start off with a simple example, a linear exponential sum. See what we get then. Fx is simply a linear function. So Fx is, let's see, alpha x plus beta. So and then, in that case, we can directly evaluate these exponential sums. A less than n less or equal b, e of n is equal to beta. So this e of beta doesn't matter. Beta. N. Okay, and that is a geometric sum. So we have a explicit expression for that. So that gives us e of beta times e of alpha, e of alpha b minus e of alpha a divided by e of alpha minus 1. Yeah, so because e of alpha n is e of alpha n. Good, and now we can use triangle inequality to estimate that. So S is bounded by, so this numerator is bounded by 2 divided by e of alpha minus 1. So that just depends on the modulus of alpha, on alpha modulo 1, and more precisely on the distance of alpha to the next integer. So this modulus here is exactly equal to e of distance of alpha to the next integer minus 1. Distance to the nearest integer. Good, and now you can, for example, use the second order Taylor series approximation of e of that term. And what you get is, this is bounded by 1 divided by distance of alpha to the next integer. So if alpha is bounded away from integers, then we get a very good estimate for these exponential sums. Only if alpha is very close to an integer, we cannot do better than the trivial bound. So yeah, so we can formulate a little lemma. E less than n, less or equal to b, e of alpha n plus beta is bounded by minimum. Trivial bound is b minus a and 1 divided by distance of alpha to the next integer. So now this can be generalized, in fact. So here we see that the derivative of this function fn is a constant, is alpha. So we can a little bit generalize this to the so-called Kussmain-Landau inequality. So if we replace that by a function f, which is continuously differentiable, the first derivative must be monotonic also. And this derivative is bounded away from integers. Then we have a similar bound as that. So to be precise, we have the following. Suppose f from AB to R is continuously differentiable. With a monotonic derivative. Satisfying. So the distance of fx to the next integer is greater or equal delta. For all x element. Then we still have a bound like that. Bounded by, yeah, what's that? Minimum e minus e. 1 divided by delta, or delta greater 0. Of course, that works for very special situations. Yeah, if we look at the graph of the function, so f prime must be between two integers. There's no other way. It cannot cross any integer. I will not give a proof of that. A very good reference for this whole theory is Graham Kolesnik, a little green book reference. Graham Kolesnik. Yeah, so just let's draw some picture. We have two integers, k plus 1. We have our interval AB. And we draw the graph of the function. So we assume that f is continuously differentiable, bounded away from the integers k and k plus 1. So the graph will be looking like that here. So this is k plus delta. This is k plus 1 minus delta. That is f prime x. Yeah, so it's not possible that this function crosses some integer. Otherwise, these conditions would not be satisfied. Huh? Yeah, f prime. Okay, thank you. Yeah, that's important. Yeah, so this works only for very special situations, but it's actually very useful because when we have a more general situation, let's say f prime monotonically increasing, but not satisfying that, we can split the image of f prime into parts, into such intervals and intervals around integers. So let's look at this situation. Suppose x is monotonically increasing. Decreasing will work the same way. On let's see, include the E, B, and now this function increases. But the image, so this is in that case the interval from f prime A to f prime B. Okay. Yeah, so the image looks like that. So now what we can do is we split this exponential sum in such a way that the images of the subintervals are precisely intervals of that form, k plus delta, k plus 1 minus delta, or k minus delta to delta. So first we split the image into such subintervals. Let's say here's k, here's k plus 1, k plus 2, and so on. So then we take small intervals. This is k plus 1 plus delta, k plus 1 minus delta, k plus delta, k minus delta. Here also a small interval, k plus 2 plus delta, k plus 2 minus delta. And then these intervals here. And we take we project these intervals back to the x-axis. That. Then this projects back to some interval. And this projects back to some interval. Here. Okay, so and now we consider the exponential sums, the partial sums over these intervals here. If we are in one of these green intervals, then we use the Kussmain-Landau bound. Otherwise, we use the trivial bound. So use Kussmain-Landau. And for these intervals, use trivial bound. For that, depending on delta, we need to calculate the length of these intervals here. Na good. So if one carries out all these calculations, one gets the famous bound of van der Kopwood, which is extremely useful. Let me state that bound. Van der Kopwoods. Yeah, so of course one needs in the end to choose the delta suitably so that one balances terms. So what one gets is the following. Suppose f from the interval EB to R is twice continuously differentiable. And the second derivative, that is phi, a bound of the form lambda less or equal second derivative less or equal alpha lambda for all x element. So then, of course, we can say something about the first derivative. So we can apply that argument. And what we get is the following bound in the end. Then sum a less than n less or equal b, e of fn is bounded by alpha, the length of the interval, d minus a, times this lambda to the 1/2 plus lambda to the minus 1/2. So this gives, yeah, I don't know, maybe I carry out the proof, the precise proof later. But so that's the idea, how to proceed to prove that bound here. Let me first give some applications of the van der Kolk bound. Okay, so in many situations, this is non-trivial. So what we need is that the second derivative is of size much smaller than 1, so that this term here is small. And also it must be greater than interval length squared. In that situation, you get a non-trivial bound here. And so this alpha is thought of as a constant. So that does not play much of a role in applications. Good. Yeah, when is this bound good? So this bound is not trivial. If this lambda, which measures the size of the second derivative, is much smaller than 1 and much larger than b minus a to the minus 2. In that range, that is good. Yeah. Certainly, you are not always in this range. So that's where this Weil-van der Kolk theory kicks in. So when we are outside this range, we can do some certain transformations to get a function eventually which satisfies these properties. Okay. Yeah, so now let's prove the exact proof postponed, or maybe I omitted. Let's deal with applications now. So that will be the standard applications in these talks, the Dirichlet divisor problem. So classical application. Of X terms, Dirichlet divisor. Another classical application which is very close to that is the Gauss circle problem. Yeah, so let's talk about that. It's about the average behavior of the divisor function. So let Dn be the number of divisors. Of n. Then we know all bound for that from O of x to the 1/2 to O of x to the gamma. No, no, let's not take the same gamma. Let's, yeah. But the O constant depends on epsilon. So if you let n tend to infinity, then this holds. Yeah, for any epsilon, but any fixed epsilon. Yeah. Any fixed, for every fixed epsilon. Maybe I just write to avoid confusion. Fixed epsilon greater 0. So, yeah. Yeah, x to the, okay, let's call it alpha also. Half. So what is the conjecture actually? The conjecture is this should hold with x to the 1/4 plus epsilon. Conjecture. O to the x to the 1/4 plus epsilon. Better, much better we cannot get. We cannot replace this exponent by anything less than 1/4, by an omega result of Littlewood. Hardy Littlewood or Littlewood only? I don't remember. Hardy Littlewood, okay, thank you. Huh?
The best is due to sound. The best omega.
Due to sound, okay, yeah, yeah. Okay. Na gut. Yeah, so this x to the 1/2 can be obtained elementarily. To get better, we need to use the theory of exponential sums. And van der Corput's bound, as we will see, gives 1/3, the Weil bound. Good, so let's carry that out, that estimate here. Yeah, so we may interpret that geometrically by observing that n less or equal x, dn is equal to n less or equal x, st, a pair of numbers with product equal to n, 1. So that is nothing else then. S less or equal x, t less or equal x divided by s. Box function. Okay, so we count pairs st such that the product of s and t is less or equal x. So we count lattice points. St square such that the product less or equal x. In other words, s or t is less or equal x divided by s. So that allows for a nice geometric picture. Take the hyperbola. Hs is equal to x divided by s. So here we have square root x, square root x, x, x. So that is 1, 1. It's this point. So what we do is we count lattice points below that, and we can cut off here, below that hyperbola. So these lattice points are somewhere here, S, T. Yeah, As I said, the circle problem of Gauss is similar in nature. Here we count lattice points inside the circle. In that case, we take a hyperbola. Good. Yeah, let's first obtain the first main term. We can just approximate this box function in the way which I indicated earlier. So we have s divided by s is equal to x divided by s plus O of 1. So n less or equal to x dn is equal to x times s less or equal to x 1 divided by s plus O of x. Good, and for that we have a good approximation. So that can be bounded using the integral test. Now good, let's draw a picture. So here's our x. So 1/2. Yeah, so this sum is nothing else than the sum of the areas of these rectangles here. And so that can be bounded from above by an integral, and from below also by an integral. So we take from below, we need to take integral 1 divided by t, 1 to x, dt is less or equal, s less or equal x, 1 by s. Okay, and we can also do an approximation from above. So when we just shift all these rectangles by 1 to the left, then what we actually get is 1 plus. And we keep that function. So then what we get is 1 plus integral. Okay, and this integral is log x. So we get x log x plus O of 1 plus O of x. Okay, so that is x. Now good, so that gives this first main term. The second main term is hidden here somewhere. We would like to exhibit it. And that we can do using the symmetry of this geometric body. So we can divide that into parts. Let's consider this part. And then secondly, that part, which is completely symmetric to the first part. So now what we can do is we count lattice points in this area with a red boundary, and then the area with this green boundary. And then we subtract all lattice points inside that square. And we get precisely the number of lattice points in that shape. N less or equal x, dn is equal to, so now we just consider the s from 1 to square root x. 1 less or equal s less or equal square root x. Again, the box function, x divided by s, plus number of lattice points in that shape is the same, so times 2, and then we need to subtract the number of lattice points in that square, 1 less or equal s, t less or equal square root x. 1. Good, and now we approximate this box function here. X. So this is x divided by s minus psi x divided by s minus 1/2. So I remind you to that definition. This is minus, okay, that is nothing else than the box function of square root x squared. So, and that is nothing else than x square root x minus psi square root x squared. Okay, and then we want also use to use a better approximation to this harmonic sum. I tell you an approximation, better approximation than just log x without proof. Proof is easy using partial summation. Yeah, so let's write this here. S less or equal x, 1 divided by s, or let's call it y. So this is log y plus gamma minus psi of y divided by y plus O of 1 divided by y square. So you can show that approximation, which is pretty good with a very small error term. And now you can plug this in, this approximation. Yeah. And then you do some calculations, which I don't want to carry out because we have not much time. What you get in the end is x log x. There's a lot of cancellation coming up. 2 gamma minus 1 x plus O of square root x. Yeah, good. Let's just see where these terms come from. So when you take 2x times the sum of s in this range, 1 divided by s, then you get precisely x log x. So that is fine. Then from this term in this approximation, you get 2 gamma. And you get, when you expand the square, an x. So this is coming up here. All other terms are just of square root x size. Okay. More precisely, you can write out this error term here. What you get is the following. And that is now important because this offers a possibility of improvement of 1 plus sum 1 less or equal s less or equal square root x psi of, it appears here, x divided by s. So just using triangle inequality gives that bound O of square root x because these are all of size O of 1 here, these summands here. Good. So since we can Fourier develop these functions, we can make progress on that using exponential sums. Okay, let me now improve that bound using the van der Corput lemma, which I mentioned earlier. So for that, we first need to make the link to the exponential terms from here. How much time? Okay, 20 minutes left, or how much I have? Okay, then I can. Okay, I can try to get this done. Yeah, so we need to look at this function. So let's call this x here. This is 1/2 minus 1/2. So that's the graph of the function. Psi x, the sawtooth function. Yeah, so this is periodic, which allows for a Fourier development. That takes the following form. For all x, not element z, we have psi x is 1 divided by 2 pi I, sum k element z, k not equal to 0, 1 divided by k, e of k z, kx. Yeah, it turns out we have that nice development of this function. Yeah. So this? Yeah, so then we need to, I mean, the way to do it is to expand. In particular, you need to expand the square here. And yeah, so retain that term here. That comes in the error term. This is also in the, yeah, okay, so this 1/2 will also cancel out. And you need this expansion here. But it takes a while. I mean, one needs to do some calculation, and a lot of cancellations occur. Eventually, only these terms remain. Some constant term and this term. Yeah. Yes. Good, so we have that development here. Yeah, so this potentially allows for reducing the problem of estimating that to estimating exponential sums of the form s less or equal square root x, e of k x divided by s. But we have here an infinite summation. We would like to cut it off at some point. Yeah, we can do that. Okay, I will remove that here. So this we should keep in mind. Yeah. Yeah, so we can approximate that by a partial sum. Sum 1 less or equal modulus of k less or equal n. 1 divided by k e of x plus. So the error term turns out to be of size 1 divided by n, distance of x to the next integer. So the error term gets worse if we approach by x, if we approach an integer by x. So if we are close to an integer, then we will get a bad approximation. Okay. So if we draw the graph of that function here, it will look like that. So it oscillates around this curve, but the oscillations become larger if we approach the endpoints. So that is even could take a bigger. Yes, so that's called the Gibbs phenomenon. Yeah. So from that we see the approximation is very good in the middle of the interval, and it is getting worse at the endpoints of the interval. Okay. Now good, so this gives already a possibility to rewrite this error term here. So sum s less or equal square root x psi of x divided by s is equal to 1 divided by 2 pi I. We pull in that summation over s, getting 1 divided by k sum s less or equal square root x e of kx divided by s plus O of sum s less or equal square root x 1 divided by n x divided by s. So that error term is quite unpleasant here, because we have to estimate how often is x divided by s near an integer. So that's very unpleasant. But there are better ways than this naive way of Fourier approximating this psi x. A very nice tool is Wahler's theorem. That says the following. So the error term will come from that here. I'm just rewriting that using exponential time. So this is from the approximation of the psi function. Yeah. So we just take a partial sum and estimate the tail by that. So some theorem says that the tail is bounded by that O term. Okay, but so it's quite unpleasant to do it like that. So there's a better tool which I will mention now. So a nicer device. To approximate psi x. It's the following theorem. Due to Wahler. There are other tools how you can do that. Every author likes a different tool. Okay, so but this is very nice here. Yeah, that element then there exists a psi star x of the form psi star x is equal to 1 less or equal modulus m less or equal m em e of x. So such a function, trigonometrical polynomial of the form. There exists a trigonometrical polynomial. Of the form such that em is bounded by 1 divided by m, so the same bound as here. So these coefficients are just inverses of the integers. And the nice thing is psi x minus psi star x is bounded by another trigonometrical polynomial. Is less or equal. So that is now a sum 0 less or equal modulus m less or equal m, bm e of mx. So that turns out to be non-negative here, that sum, where the bm's are of a very special form. Yeah, bm is equal to 1 divided by 2m plus 1 times sum m less or equal m, 1 minus m divided by m plus 1 e of mx. What? BM. So what I wanted to say. So one moment, I need to check. Yeah, okay, simply that, yes. So did I get everything right? Yes. Yeah, so in fact, this is a fair kernel here, divided by that term. So the fair kernel is non-negative. Yeah, so the advantages we have, not this ugly term here. We don't need to deal with s such that x divided by s is close to an integer, like here. We have just approximated psi x using two trigonometrical polynomials, where the coefficients are nicely bounded by 1 divided by modulus of m. Okay, and here the coefficient is simply bounded by, oh, sorry, that's not the sum. 1 minus m divided by plus 1. So that is simply bounded by 1 divided by m, which is also bounded by 1 divided by modulus of m. And that should be an m. So, okay, and that should be an m here also. Okay, so now it's correct. So do I still have? Huh? Here? Yeah, bm, that's a small m. Yeah. Yeah, that is capital M. So here's capital M, here's small m. So, yeah, this is a constant here. But we can take any capital M. And yeah, so if you draw a graph of that function here, that as a function of m, you get something like that here. Like that, yeah. Good. Okay, so now there's still a bit of time left. Let's just rewrite this error term here using Wahler's theorem. So we need to write that. Good, so I remove that from the board. So s less or equals square root x, psi of x divided by s. So this is s less or equals square root x. Psi x divided by s plus psi x divided by s minus s. Is bounded by, we use the triangle inequality, s less or equal square root x, psi star x divided by s, plus, we can pull in the modulus here, s less or equal square root x, psi x divided by s minus psi star x divided by s. And now we can replace this by this trigonometrical polynomial, getting less or equal square root x em e of x that plus square root x. And then we use that bound here. Divided by s. So this should be x divided by s. X divided by s. Good, and then we can rearrange the summation. So what we get is and we can use the triangle inequality, getting em em So here we have a term coming from 0, but B0 is also estimated by 1 divided by m. So we get this is bounded by 1 divided by m times, so for m equals 0, this is just a trivial sum. So we get square root x divided by m plus, good, and for modulus m greater or equal 1, we can combine these two terms, and what we get is sum 1 less or equal m less or equal capital M, 1 divided by m, s less or equal square root x, e of mx divided by s. And by symmetry, we can also just remove this modulus sign here, because yeah, for m and minus m, this will be the same when we take the modulus. So we can remove that here. So, and now we need to use Van der Corpus bound to estimate that. Then we calculate what we get, and then we choose m suitably. So that I will do in the next lecture then. Okay. Thank you.
Thank you very much for the lecture, Stephan. Are there questions?
Yeah. So we get 1/3 actually. We get an improvement. And then we will see how we improve the 1/3. Hmm? What? No, that's the limit of that technique. Yeah. And exactly, we need better bounds for exponential sums themselves to improve the 1/3 exponent.
Other questions? If not, let's thank Stephan again.
Okay.